Okay,
Inshallah.
so inshallah. Today we'll start chapter 1. Last time I talked about the syllabus of the course and the requirement and the assessments, and also I gave you suggested dates. Now, chapter 1 is about just introduction to vibration, and here we will get to know the importance of this course and the subject in mechanical engineering for mechanical engineering students. Okay, so first of all, the definition of vibration. It is defined as any motion that repeats itself after an interval of time. And there are either we call it vibration or we call it oscillation. They mean the same thing. So it is a type of motion, a specific type of motion that repeats itself. It's oscillatory sometimes we call it, or oscillation, or vibration. So it is part of dynamics because dynamics is to study motions, but here it is specific part or a specific type. The other thing, in order to have oscillations, it means you should have a system rather than an object or a particle. So all bodies possessing mass and elasticity are capable of vibration. This is one of the systems that consists of mass and elasticity. That elasticity comes as from the spring, or from if you have a beam, elastic beam, then it will have both things. It will have the mass and it will have the elasticity. Or if it is a spring mass system, that a mass or a lumped mass supported by a spring then becomes a system that can vibrate. Now, most engineering machines and the structure will experience vibration to some degrees because they have they consist of their mass is not neglected, as well as that they have elasticity. So machines, structures, members like beams or cables, or the casing of machines, whatever. Those will have mass and elasticity, and then they can vibrate. Okay, in dynamics, we focus on rigid bodies or particles or rigid bodies, in which they don't have any elasticity, or they will not bend, or it will not deform with time or under load. So those objects, rigid bodies, will not vibrate unless it is part of a system. But most of the machines or structures, they have a certain flexibility or elasticity. Then they will vibrate. Okay. Okay, so when we talk about vibration, then there is amplitude, there is frequency, and those should be calculated before manufacturing. So part of the design is to consider the oscillatory behavior of the systems or machines. Okay, so suppose you want to have a shaft driven by a motor, or impeller driven by motor, then you have to study the vibration of this machine, and what is the required or the safe operating frequency, so that you don't have any damages to the machine. Okay, so vibration will always be available, or machines will have vibration, either as free vibration or as force vibration. So the vibration will not be eliminated 100% because it is a physical phenomenon. When a system is constructed with mass and elasticity, then you cannot avoid to have the system not to vibrate. Okay, so the systems will vibrate, and then you can control the vibration, but you cannot eliminate 100% the vibration or prevent machines or structures from vibration. So you can design the system to work or to have safe vibration, okay, or acceptable. Examples of systems are swinging of a pendulum and motion of strings, cables, or motion of beams. Okay, spring mass system, which is the car can be modeled as a spring mass system when vibrating in the vertical direction. Torsional vibration of shafts. Shaft can, as you did in mechanics of material, shaft can be twisted. Okay, and when the twisting is occurring in both direction, let's say alternating, then becomes oscillatory motion. So we call it torsional vibration. Okay, here are the representation of some of the examples and of systems. The pendulum, this is called simple pendulum. It means there is compound pendulum as well. The simple pendulum is a pendulum that consists of bulb mass. A mass here, as you can see, is called a bulb mass. And there is no description of this mass. I mean, there is no dimensions are given. No dimensions are given. And the chord is assumed to be massless chord. Then we call this system as simple pendulum because the bulb mass, it is a point mass. It's considered as point mass. That the diameter of the shape is not given. And this is the type of pendulum which is called simple. There is compound pendulum when the chord is replaced by a rod, and the rod is not massless, or the mass is not a bulb mass, it is a disc with a given diameter, or it is other type of objects. Okay, but either simple or compound pendulum will oscillate. Okay, we have spring mass system. Again, this is a system that can vibrate. The mass, as you can see, is just represented by a box, which means it is rigid. And again, this is point mass. And it will only vibrate in the vertical direction. Okay, that's assumptions, right? It is only vibrating in the vertical direction. And the spring with the stiffness. So it is not rigid, it is elastic. The combination of the two makes a system that can vibrate. And the torsion of shaft, we have the rod or a shaft here with a certain length and given diameter and of course material, and a fix here. and attached with a disc at the free end. And here we have a rigid attachment between the shaft and the disc. If you allow only torsional vibration, it means there will be oscillation about the vertical center line of the shaft. Only angle of a twist here, theta. And that becomes torsional vibration. So those are three examples of systems, and any mechanical system will be modeled as one of those systems. Okay, so in order to have a system that can vibrate, there are elementary parts. There are three main parts, but the first two, which is mass and spring, are essential. So mass, when there is spring mass system, or inertia for the rotational or torsional. Okay, here it is called rotational. And here is a torsional. They mean the same thing. There is angle of a twist or angular displacement. Okay, this is a translational system. Okay, so the elementary part of any vibrating system should either consist of mass or inertia. Mass for translational system, inertia for rotational or torsional system, spring or elasticity. Spring, if you have helical spring, okay, or you have a member that already have elasticity. And it can be represented by spring stiffness K, which is a Newton per meter for translation or linear system or linear spring, or it is a Newton meter. Per radian. So either for this, and this is the unit for K, Newton meter per radian for torsional, for the shaft. And number three is may or may not include a damper. And here the damper is can be viscous. Okay, the purpose of having a damper in the system is to reduce the vibration with time. With a system made of 1 and 2 elements, okay, or parts, there is an assumption that the vibration will not stop or will not decrease with time. With adding a damper, if you have a viscous damper, then you can control how the decay of amplitude with time. Okay, that you can make it fast decaying or slowly decaying. So a viscous damper, if it is added, it will work as an energy absorber that absorb energy or dissipate energy from the system, so that it will its vibration will decrease with time. And here, as you say, it is may or may not. This is not necessary to have a damper for a system to vibrate. Okay, system once it has mass or inertia or spring or elasticity, it will be capable of vibration. Now, the viscous damper, we can see this in the suspension of vehicles or motorcycles. And it is, in fact, made simply of a cylinder. And inside it there is a piston. And here it is a rod. And there are holes inside, or there are holes made in the piston. And the oil, there is oil or fluid on both sides, which is filling the cylinder. The cylinder, if you make the cylinder fixed, okay, then the motion of the piston is resisted by the velocity, or the piston will resist the velocity. So it is there is a relationship between the force applied, F, and the velocity of the piston. Okay, so F is directly proportional with the velocity. And that relationship is linear. Okay, so we have the representation of a viscous damper is this type. You know, this is the way to represent or schematically show there is a damper involved in the system. And this, of course, the spring. Okay, so we have spring and damper. This is called actual system. And this is called the model. That with assumptions, some assumptions are made to come up with a model that we can apply a mathematical expression, and then we can find equations of motion and the solution. So actual system consists of many things, and we can just approximate to a model. Okay, the vibration in the vertical direction, that the rider and the body of the bike is just a mass, rigid, and then suspension is just equivalent to spring and damper. K is used to represent the stiffness of a spring, and C is used to represent the constant of the viscous damper, and EQ is mean equivalent. Okay, so we have K, it means equivalent stiffness. And CEQ, it means equivalent damper constant or damping constant. Okay, equivalent, we will see the meaning of or how to obtain equivalent value. Okay, this is a table that shows the stiffness of some elements. We have, spring is characterized by its stiffness, a spring constant, or it is given as K. And for some members, if we go directly to the helical spring here, which is the familiar a common spring, then you can find the stiffness, the relationship between the force and the displacement or the change in length in the spring is given by Hooke's law. So that we have F equal to Kx. X is the deflection. And K is the constant of a proportionality, or the spring constant, or it's called the stiffness. This is the design equation. Okay, so you can find the stiffness of any given spring from this equation, which is K equal to G d to the power 4 over 8 n d to the power 3. The small value, the small d, is the wire diameter, because a spring is made of wire and made as a coil. Okay, so d is a wire diameter. Capital D is the mean coil diameter, and n is the number of active turns between the 2 points of load. Okay, so this is the load point, and this is the second load point. So you count number of turns. Okay, number of turns, it means the helical spring is rubbed as a coil. So it is made to rotate, or I mean turn. There are turns. Okay, عدد اللفات يعني turns. So you can number of turns 1, 2, up to from the first load point to the second load point. So a spring can be, this is a spring. It depends on where is the load point. If you have a load point here and here, then here is active. Spring is active. The other part of the spring is not active, or it is not loaded. So the load or the force is carried between the load point, which is point 1 and 2. So active turns means you count the number of turns between point 1 and point 2, which is the load points. Okay, that's called the N, number of active turns. Now, other members, for example, the rod, the spring stiffness, if the rod is under axial loading and the rod is flexible because it can be made of one of the materials like steel or aluminum or copper, then it will elongate under load. Okay, and there is a relationship between, you can get the relationship between the force and the deflection, and you arrange the equation as Hooke's law, which is F equal to Kx, then the constant multiply, or the expression multiply by X is stiffness, which is for the rod is EA over L. So this is the K equivalent if you have a rod under axial loading. E is the modulus of elasticity, A is the cross-sectional area, and L is the length of the rod. So if the length, this is K is inversely proportional with length. So you can make the spring or the rod flexible by making the rod long, or relatively long. And here is tapered rod, and K equivalent is pi ED times D over 4L. And we have beams. Here is fixed beam. And fixed beam, you will find this is a force at midspan, F here, at midspan, and the total length is L, and this is at L over 2. Force is applied at L over 2. The flexion, as you did in mechanics of material, deflection of the beam under concentrated load at midspan will depend on the value along or the location x along the beam. Okay, so here is x along the beam. And then the beam will deflect, right? Deflect this way. So y is a function of x. At x equal to 0, then y 0. At x equal to L, y 0. And y is maximum when x equal to L over 2. So this equation is obtained from the moment equation, which is d square y by dx square equal to m over ei. And then you can integrate it twice to get y as function of x. When you put x equal to L over 2, then y is the deflection beneath the load. Okay, you can call this one my y maximum. And then you will have a relationship between f and y maximum. Okay, and this can be represented as a spring. The spring mass, the beam, can be modeled as a spring by considering x equal to L over 2. Okay, so y maximum is equal to y when x equal to L over 2. And then you can get Hooke's law equation from which you can find the stiffness as 192 EI over L cube. And here another example is shown is the cantilever beam. A cantilever beam with a concentrated load at the free end, fixed here, and this is the load at x equal to or at L at the end. Again, deflection will depend on x, but since we need the equivalent stiffness of the beam at the free end, we will put x equal to L, and then F will be proportional with the maximum deflection at the free end. Okay, and then you can get the K equivalent when you arrange the equation for deflection as Hooke's law. Yeah. Any question? Okay. Aqil, you have a question?
يا دكتور، كنت بسأل الحين قيمة الكي في آخر مثال، هذه تنطبق على لو طبقنا الفورس على أي مكان على البيم ولا بس في النهاية؟
الكانتليفر بيم؟
إيه.
ولا كانتليفر بيم؟ اوكي، لا بس في النهاية.
يعني اللي فوقه بعد المثال قبله بس حق اللي كان الفورس في الأوفر 2.
بالضبط، بس ايه.
اوكي.
Okay, so this value of K will depends on the type of the boundary conditions of the beam and the location of the force. Okay. Yeah, this is the way. Okay, so otherwise, if you have a force somewhere here, then this equation of stiffness will be not the same. It will be different. Okay, so for a cantilever beam, the stiffness is 3EI over L cube. This table is, we will use it whenever we need it. So because what we will do is we study actual systems and we will model them to spring mass system. So if you have the third type is simply supported beam. Okay, simply supported beam, K equivalent is equal to 48 EI over L cube. Okay, so as you can see, all of them, there is EI over L cube, but only the coefficient here is different. 192 for the fixed beam, and 48 for simply supported beam, and 3 for cantilever beam. Okay, so when you have an actual system, and here there are shown two types, a fixed beam carrying electric motor at mid-span. And another example is a cantilever beam carrying electric motor at the free end. So those are called actual system. Yeah, we have to make assumptions in order to find the equivalent system. Okay, so that you can apply the mathematical equations. So as an example, a cantilever beam here, this actual system is a cantilever beam carrying a mass at the free end. The beam is not rigid. As you can see, there is E, which is elasticity, and a cross-section, and I. Those three values will determine the value of K. And of course, how the beam is supported. This is a cantilever beam. So this is equivalent to a spring mass system with spring stiffness K equivalent, or K is a 3EI over L cube with the mass attached at the free end of the spring. And the spring is fixed from the other point. Okay, so this is the spring mass system, which is the equivalent, or it is called model. And the model is made with a lumped mass, assuming that the mass of the beam is neglected. Okay, neglect the mass of the beam. Okay, this is one of the assumptions. Okay, and in chapter 2, we will see what we can do with the mass of the beam. Okay, so usually whenever you have a spring mass system, the spring is assumed massless. Okay, and the vibration will be in the vertical direction. As you can see in the actual system, this shown here, X, this is called variable, or the coordinate that describes the motion of the system. Okay, which is the motion at the free end. Now, usually we use X, and you can use Y if you want. Okay, X, usually in mechanics of material, you will take it along the beam. That is X, right? And then the vertical deflection is taken as Y or W. It's just a matter of names, but in vibration, we usually use X or we use Y, but that means the coordinate of motion. Okay, the variable, which is x here. X of t is the displacement of the mass, which is the end, which is attached at the end of the beam, and it is the same here. Okay, on the equivalent system. Okay, some of the notations, terminologies is the degree of freedom. Remember, we are talking about systems, not objects. The number of masses in the system will determine the number of coordinates used. Okay, and the number of springs as well. So the definition of degrees of freedom is the number of independent coordinates required to describe the motion of a system is called degrees of freedom of the system. For a spring mass system, which is shown here in part B, either horizontal system or vertical is the same. Okay, here there is only one coordinate is required. Okay, assuming that the mass of the spring is 0, massless spring. Then only x is enough to describe the motion of the whole system, which is the mass and the spring. The spring is fixed at the top, so its motion is 0, and it is massless. Then we don't need to know how much it is changing here along the spring, because this is massless. We just need x at the end of the spring, which is attached with the rigid mass. Okay, and the mass is rigid, then it is x is the motion of the center of gravity of the mass, or it is considered as a point mass. Okay, so the mass is point mass. And 1 point is required. Okay, so this x is called coordinate, or it is the displacement, which is it is only 1, and it means there is 1 degree of a freedom system. It is called single degree of freedom system. Single degree of freedom system. And for part example C, torsional system, theta, if there is only the rotation is about the center line of the shaft. Theta is the angular displacement, which is the angle of a twist of the shaft. And there is no swinging here, then becomes a single degree of freedom. Theta is enough to give the description or the motion of the system. For part A, there are 2 coordinates shown, x and theta. Now what you can see here, this is a rigid link. And it is pinned to fixed support. This is fixed. Okay, and this is pin connection. And we have a rod from here to the end. Again, it is hinged at the top, which is fixed here. And this is the mast. Okay. And assuming that the rod is massless, and also the rigid link is massless rigid link, then this becomes a single degree of freedom system. Okay, here is a spring with a stiffness K. Again, it is massless spring. X and theta are related. If you put length of the rigid length, you put equal to L. Okay, then X equal to L sine theta. L sine theta. X and theta, this is true for all values of theta. Then this is called relationship equation. This is the relationship between X and theta, which means X and theta are dependent. Therefore, the system is single degree of freedom system. I'm going to abbreviate it 1DOF, which means single degree of freedom system. Okay, so this is the definition of degrees of freedom. It is the number of independent coordinates. Number of independent. Here we have 2 coordinates shown, but those are dependent. To give the vibration can be given in terms of theta or in terms of X, and become single degree of freedom system. Here is 2 degrees of freedom system. Examples of 2 degrees of freedom system. We have M1 and M2. Those are 2 lumped masses or point masses, and fixed by or connected by springs, and there is one spring here, and this is a fixed point. So the system can oscillate. M1 is given a coordinate x1, and M2 is given a coordinate x2. X1 and x2 are independent. Okay, because there is a spring in the middle between them that join the 2 masses and makes the coordinate for each mass might be not the same. X1 and X2 are not the same, and X1 and X2 are not related by any algebraic equation that is valid for all time, as we have seen in example A here, that X equal to L sine theta. Okay, this is the dependent equation. Here we don't have a dependent equation. The 2 masses are coupled dynamically. It means during vibration, M1 will have effect on M2, and M2 will have effect on M1. Okay, the same thing for the shaft that carries 2 discs. The shaft is flexible, so it can twist, and the angle of a twist theta 1 on one end is different than the angle of a twist on the other end. So there is theta 1 and there is theta 2, and theta 1 and theta 2 are not necessarily the same. So this becomes 2 degrees of freedom. And here we have spring with mass, and then with the mass there is a pendulum attached. So you can, X is for the mass, is the motion of the mass, but the pendulum can be either described by theta or y, or even x, small x. But those 3 are related. So you can write y equal to L cosine theta, and you can write small x equal to L sine theta. So for the pendulum, you can choose just one of them, one of those variables, because those are the dependent. And there are 2 dependent equations between y and theta, and x and theta, or even x and y, because x squared plus y squared will equal to L squared. Okay, we have one more equation. So those are the 3 dependent equations. Okay, the dependent equations mean that those variables are dependent. So one of them is enough. X is the motion of the mass, and small x or y or theta can be used to describe the motion of the pendulum. Okay, and the number of degrees of freedom will get higher and higher as we have more masses separated by springs. Okay, so there is M1, M2, M3 here, and there are between M1 and M2 there is a spring with stiffness K2. Between M2 and M3 there is a spring with stiffness K3. M1 is supported by K1 and so on. So this makes a 3 degrees of freedom system with the 3 independent coordinates x1, x2, and x3, and the same thing for the system shown here, which is rotation. With the 3 disks, then you can have 3 degrees of freedom: theta 1, theta 2, theta 3. Here, 3 simple pendulum are joined, but and for each pendulum you can get x1, y1, and theta 1. And for the second pendulum, it is x2, y2, theta 2. And for the third pendulum, it is x3, y3, and theta 3. But for each pendulum, the 3 coordinates are related. So x1, y1, and theta 1 are related. You can choose one of them. And x2, y2, theta 2 are also related. And then you can just choose one coordinate. The same thing for the pendulum number 3. So it is 3 degrees of freedom. And the number of degrees of freedom can increase this way. You can add mass number 4, and then becomes 4 degrees of freedom. If you have, if you put a mass after M3, and separate them or join them by spring. Okay, and until we reach to a continuous system. This is called continuous system. Which means that the mass, this is a cantilever beam, with the mass of the beam is not neglected. It means at any point on the beam, there is part of the mass of the beam. Okay, and this makes the system to be has infinite number of degrees of freedom because it is elastic as well. So this is elastic with E and the cross section A and moment of inertia I. Okay, and L as well. There is length L. And the mass is not 0 with M. So this makes the system to be and has infinite number of degrees of freedom. Okay, so you can you can give discrete points on the beam. So here is x1, x2, x3 until you get a very large number of points. Now we gave an example at the top about spring. I'll go just above here. This example is a beam supporting a mass at the free end. So if the beam is neglected, if the mass of the beam is neglected, then we don't have infinite number of degrees of freedom as this one. But if the mass of the beam is not neglected, it means there are infinite number of degrees of freedom. The importance of identifying the number of degrees of freedom is to find the resulting frequencies. So for each, if you have a system that has only 1 degree freedom, there is only one frequency of oscillation of the system. If the system has 2 degrees of freedom, it means it will have 2 frequencies, two different frequencies of oscillation, and so on. So the number of frequencies involved in any system will be equal to the number of degrees of freedom. Now, what we will do during the course, this is the idea of increasing the degrees of freedom, but the analysis will be complicated as you go more than one. So we will do most of the course from chapter, chapter 2 is the start of analysis, is the free vibration. Up to chapter 4 will be about single degree of freedom system, which is 90% of the course will be about single degree of freedom. And test 1 and test 2 will be about single degree of freedom. This is the fundamental thing. If you can understand single degree of freedom in this course, and then by the end of the course, I will introduce 2 degrees of freedom and more. This should be easy for you to understand higher degrees of freedom and also the continuous system. Okay, so next time we will talk about classification of vibration, and this is the last slide, but I will keep it for the next lecture. Any questions?
دكتور
Yes.
لما تكلمت عن elementary parts في البداية قلت ان يعني الحين اذا ممكن ترجع فوق دكتور ما عليك امر.
ان شاء الله. اوكي.
اي هني في الانرشيا ليش الوحده دكتور الكيلوغرام دوت متر سكويرد، هاي الماس مومنت اوف انرشيا.
ايه هي ماس مومنت اوف انرشيا، بس باختصار انا كتبتها انرشيا.
اي بس قصدي يعني مو الجي المفروض هاي حق البولر مومنت اوف انرشيا.
ايه هي هاي بولر ماس مومنت اوف انرشيا. بولر ماس مومنت اوف انرشيا.
تمام اوكي.
دكتور شنو الفرق بين moment of inertia and mass moment of inertia؟
مومنت اوف انرشيا في عندك اريا مومنت اوف انرشيا يسمونه سكند مومنت اوف اريا.
اي
اوكي، او سكند وعندك الماس مومنت اوف انرشيا. area moment of or second moment of area that will give you the stiffness of a member, and that is related to the cross-sectional area of a beam or a member. But mass moment of inertia is it is related to dynamics. Okay, so if you have a moment of inertia and you apply a torque, and then this will allow the, let's say, a disk to rotate at certain angular acceleration. But when the moment of inertia is higher and you're applying the same torque, this will have less moment of less angular acceleration. So it is related to dynamics, or you can say this is resistance to rotation. So it is related to dynamics and to rotation. But the second moment of area is nothing to do with dynamics.
واضح دكتور، شكرا.
It only represents the stiffness. It is geometrical value. Okay. Also, mass moment of inertia is related to geometry, but beside geometry, it is also the mass, and you know that the mass is related to dynamics, because sum of moment equal to J theta double dot, or J alpha. Okay, so we use I here for the second moment of area, and we use J as the mass moment of inertia, or polar mass moment of inertia. اوكي any other question؟
دكتور بس بغيت اسالك اذا بتنزل نوتات بتسيف النوتات اللي كتبتهم انت الحين دكتور.
النوتس موجودين في التيمز في الفايلز، واللي تشوفه في الون نوت موجود محفوظ، يعني هذا اللي تشوفه ما يتغير موجود. بدش على الون نوت تروح لشابتر 1 لكتشر 1 بتشوف هذا الشيء موجود. يعني كل طالب
يعطيك العافيه.
ايه كل طالب يقدر يشوف ذا الشيء، بس ما يقدر يكتب عليه يعني، بس انا اللي اقدر اكتب عليه هنا في هاي الصفحات، بس عندكم صفحات ثانيه تقدرون تكتبون فيها. يلا مع السلامه.